All right, so definite integrals. They're different than indefinite. But what we have here, just a few little notes. Integration can be used to find area, volume, central points, many useful things. So integration has lots of purposes. Area is the biggest one that we're going to study, but volume, centroids, center of mass, fluid pressure, net change. You can do lots of things with integration. So what we're looking at today is not actually just finding the original function, but we're going to look at how we can find the area under the curve. So if you look here, here's a little visual. We want this area. So like in geometry, you can find a rectangle, a triangle, a trapezoid. With calculus, we can find the area of shapes that have curves versus straight edges. Another thing to look at is if we were in class, we would do a little lab with this, but basically dx in our differential equation with area stands for slicing little pieces of this. So a long time ago, what we did is we tried to figure out if we put a whole bunch of little rectangles in there, how close could we get to approximating the area? Then somebody else said, well, what if we use trapezoids? Basically, the smaller the width of the rectangle, this dx, the smaller that width, the closer we get. Same if we were using trapezoid method, things like that. What we're going to look at today is just kind of the notation. We're not really going to use a lot of calculus today besides just the notation and some basic geometry. So the notation, the integral symbol, which I called an S, which makes sense here because it can stand for the sum. The idea of adding up a whole bunch of little pieces to get area. So we have our integral symbol, the function we want to integrate. This dx, remember that's all those little tiny rectangles, or just the area combined. So it's that sum of a bunch of things, a bunch of rectangles, to get your area. After that, let's look down here. So the difference between indefinite and definite, a definite integral has start and end values. See here where I have a and b? Here is our indefinite, which we've done. There's no end values. So these end values, you can call them limits, bounds, boundaries, interval. I use the word interval a lot. So the interval between A and B, what is this area? And we're going to look at what happens when we change that interval, things like that. Okay, so first of all, let's talk about some properties of definite integrals. So a definite integral, here I have a sum and difference. So just like with indefinite, if you're adding f and g together, those two functions, it would be the same as if you did an integral for f. So you found the area for f, and you found the area for g, and you added them together. So if I look over here, if I wanted the area of this half circle plus this triangle, like if this was f and this is g, I would find those two areas and add them together. All right, the constant, this k in front, it just means that you're going to still find the area of the function on the interval a to b, but once you find that area, you're going to multiply it by whatever k is. So if you found this area here was 4 and k was 3, you would take 4 times 3. Your area would be 12. The reverse function. So this one looks like, let me hit pause for a second so I can pull up Desmos to show you exactly what. Okay, so on Desmos, I have an integral, and I'm going from 1 to 4. You can see right here my a and my b, and I'm going from 1 to 4. The area is 20.1. The area under the curve is the shaded area. So what happens if I reverse a and b? So I'm going to make a 4 and I'm going to make b 1. So remember this 20.1 so you can see the difference. So a now is 4 and b is 1. So what happened? It's the inverse, and that's what it is. It's the negative value of that. So if we go back here, we can write that that is the negative value of a to b of f of x dx. The next one, the 0 one, is really easy. If you have a and b, your limits are the same, it equals 0. I think you might have, if I probably went through it pretty fast, but right here, if I change both of my a and my b to the same number, look at my area, it's 4. Notice there's nothing there when I have the same number. So there's no little triangles or rectangles or trapezoids underneath there. Okay, so if we go back, Then our last one says by parts. So this one, I'm going to use this little diagram over here. If I add the semicircle and the triangle together, I could find each of them separate. Their values separate will equal the total. So from A to B and B to C is the same as saying from A to C of that function, as long as we're talking about the same function. Okay, all right, so let's try to use some of these here. So this is an example. It wants you to evaluate this, and they gave you all of these. So the first one they give us is x squared is 26 thirds. Well, if I go here, I have negative x squared. So again, my 1 and my 3, my boundaries are the same. So this is just using these properties we just went through. So my first one, mine would be from 1 to 3 of negative x squared dx. Using the given information, that would be negative 26 thirds, because this one was positive. My next one is from 1 to 3 of 4x plus 4x dx. So I'm going term by term. So x is 4, so 4x would be 4 times 4, which is 16. And then my last one is from 1 to 3 of negative 3 dx. Well, dx itself is 2, so negative 3 dx we would multiply, because that's a constant or a coefficient. So negative 3 times 2 is negative 6. So then to get your answer for this, you would add all of these. So you're going to add all of those. You might have to get your calculator to add, but that is 4 thirds. All right, so let's look over here at this picture that I have, this geometry picture. Notice, first of all, time out, let me go back to Desmos and show you. We talk about the area under the curve going to the x-axis. So if I did this again, notice that I'm going to the x-axis. It stops at the x-axis. What happens when your function is below the x-axis? So I'm going to change my function. I'm just going to do just a line, a linear function. So I'm just going to do 2x plus 1. So here's 2x plus 1 from 1 to 4. But what would happen if I change my boundaries and I have negative? So let's do that. Let's go from negative 1. Ooh, look at that. See how it's blue now? To, let's just let B be 0. So there's negative 1, or negative 2 to 0. My area under my curve is negative 2. It's negative because it's below. So using my diagram, red is positive, blue is negative. So anything below the x-axis still goes back to the x-axis. It's just a negative value. And that can happen with any function. It doesn't have to be just a line. You could have a quadratic that is below the x-axis. So this blue area is negative. It's not negative area, it's negative because of its placement. The red area is positive because of its placement. So again, it's not technically negative area, it's where it's placed. So below the x-axis is negative, above is positive. All right, so let's look at this geometry figure I have here. The first one, I'm asking you to find the area from 4 to 6. So we're looking from 4 to 6. So here's 4, here's 6. What type of shape is that? Could you find that area? Without knowing any calculus, could you find the area? Well, it's a triangle. So my base is 2, my height is 2. So the area would be 1/2 base times height, which is 4, which is 2. Okay, and so our next one, we're going to look at, all right, so the next one goes from negative 4 to negative 2. So that's right here, negative 4 to negative 2. Again, what shape is that? It's a triangle. All right, so you would have a base of 1, or a base of 2, I'm sorry, a height of 1, and then you'll take half of that, and so that would just give me 1, but technically, remember it's below, so it's going to be negative 1. All right, then we have the area from negative 2 to positive 2. I'm going to change color. This is a little different. So negative 2 to positive 2. It's a semicircle. So a semicircle would be pi r squared divided by 2. What is your r? Well, your r would be, it looks like 2. My radius is 2. So I would get 4, because 2 squared is 4, divide by 2 is 2, so I get 2 pi is the value of that, but it would be negative because it's below the x-axis. Okay, then the last one says from negative 4 all the way to 6. So you're going to go from negative 4 all the way to 6. Okay, well we know that this one was negative 2 pi, and we found out this one was negative 1, so we already have that. We know that this piece is 2. What would this piece equal? Well, that piece would still, it's a 2 by 2 triangle, so 4 divided by 2 is 2. So what you do then is you just add all those up. So we have negative 1 minus 2 pi, so I got those, plus 4, which is 3 minus 2 pi. And that's using geometry to evaluate definite derivatives and also using their properties. So there's a WebAssign that you're going to look at, and that you might have to use some geometry. You might have to use these properties. Some of them will just show you something and ask you like what should your A and B values be by looking at the picture. So go ahead and go to WebAssign and complete that assignment. Email me if you have any questions. Have a great day.